This is the AB 6.1 to 6.3 review. Calculators are allowed, but you're not going to need them. And all three parts of this problem deal with whether or not you can set up a generalized sigma notation sum for an approximation of a volume. So we did a little bit of this earlier on the non-calculator part. I think it was number 4. And what we're going to do now is kind of see if we can write this for a general form. So the first thing we're going to do is we're going to start just with the graph. So the graph on this, we have a calculator, so we could plug that 4 minus x to the 3/4 into our calculator, and we could see that when I plug in a 0, or excuse me, yes, when I plug in a 0, I'm going to go up to 4. Sorry, I had a 1 there. I'm going to go up to 4, and when I plug in a 4, I'll have, oh, I don't know for sure. We'll have a 4 through it. It's not going to come out easy, but it'll probably be a number somewhere around 1. So we can go out 1, 2, 3, 4, and we're cutting it into 8 subintervals. So that means we've actually got 8 of these, and we're ending up at 4. So we can see on our graph, if we graph it on the calculator, that it actually is a concave up curve. And that might come into play if I want inscribed versus circumscribed. So make sure that on the test you graph this function to see whether it's an increasing or a decreasing concave up, concave down, because that shape of it is going to determine how you draw your rectangles. So the volume of the solid is going to be estimated by partitioning and then slicing with planes that are perpendicular to the x-axis. So I'm going to draw each of these little slices here. And what's different with this problem is that instead of actually finding the x-coordinates, we're going to label them with subscripts of x. So this first left coordinate is going to be x sub 0. This will be x sub 1, x sub 2, x sub 3, all the way up to x sub 8. And we're going to write these approximations using sigma notations and x sub i's. So that means all 3 of these are going to be variations on this sort of setup. Since I'm going to take one strip, whichever strip it is, and I'm going to rotate it around the x-axis, I'm going to have a cylindrical disc that looks something like this. And the radius is going to be a function value. So the volume of that disk is going to be a pi times an r squared times a delta x, and then I'm going to add them up. Since I have a limited number of them, I won't do the sum, the integral symbol, because that's for when I have an infinite number. When I have a finite number, then I'm going to use the finite width and add them up using sigma. So they're all going to look something like this, and let's recall that that radius is actually going to come from the function value evaluated at one of these x's. So that means they're going to look something like a pi times a y of an x sub I that has been squared times a delta x. So every single one of these is going to look something like this format. Our job is to figure out, number 1, what delta x is, and number 2, what comes out of y when we plug an x sub I in, and number 3, what those i's are going to start and end with. So if we look at part A, it says I want the approximation produced with inscribed cylinders. So inscribed means for each of these subintervals I need to take the lowest y value. So if I do inscribed, I'm going to be starting here and do right edges. And each of those will be smaller and then plugged in to create the height or the radius of that cylinder that gets wrapped around. So in this particular case, I will take this setup and I will figure out that the first edge that I use is a 1 and the last edge that I use is an 8. So I is going to start at 1 and go to 8. So that means if I do it for this particular problem, I will have a pi times the output, which is a 4 minus that x sub I raised to the 3/4, and that will all be squared. So I've done a pi times the output of the function squared times the delta x. Well, looking up here, my delta x is 4 minus 0 over 8, which is a half. So I'll have a half here, and that's all I have to do is write the sigma notation for that, and I'm done. Oh, sorry, that was all underneath. Let me run through that again. I have a pi, or I'm taking this notation, and I know that my I starts at a 1 and ends at an 8, so that's my low and my high I. And then I just figured out what delta x was. It's a half, and I plugged that x sub I into, actually this squared should be on the outside. I plugged that x sub I into the function, so I got a 4 minus an x sub I raised to the 3/4, and that was all squared. So now let's look at the next one. I want circumscribed this time. So if I circumscribe, that means with each subinterval I want to take the highest y-coordinate. So notice that in this case I'm going to the right from the left edge. So I'm going to start with that x sub 0, and the last one I'm going to use is going to come from the 7. So it'll look exactly like part A, except those i's are going to start and stop at different values. So the starting place on this one is 0, and the ending place is 7. Okay, last part, C, I want the midpoint. So let's think about how we find a random midpoint. Any midpoint that I want is going to be the average of these two. So that means the thing that gets plugged into the function to create the radius of the cylinder is going to be the midpoint between the x values. So that means down here I'm going to have that same setup with a pi times a radius squared times a half, only this time my radius will be y with an x sub I plus an x sub I plus 1. So I have the adjacent x values and I divide them by 2. So that's going to be my middle of those two x coordinates. So for any slice that I choose, this would be the midpoint x coordinate that gets plugged into the function. So if I finish that up, it's going to be a pi times, I want to plug that into the original function, so that's a 4 minus this messy x coordinate raised to the 3/4, and then I square it and multiply by delta x. So the only thing remaining is to figure out what these should start with. So let's think about that first and the last midpoint. If I want the first midpoint, I need to add x sub 0 and x sub 1 and then divide them by 2. So that means down here my first one is going to have I being 0, and then that 0 plus 1 gives me the next one. So I is going to start at 0 on this one. If I want to find out where I ends up, we got to go to our last interval. So on the last subinterval, that midpoint's going to come from x7 plus x8. That means down here I need this to be a 7 and this to be an 8. So we can see that the I is going to end at a 7. And we're done.